Okay, so this is exercise 4 of the diagram window course. And in this exercise, we're going to practice a couple of the things that we just got done talking about. So specifically, putting child diagram windows onto a main diagram window, and then also adding some buttons that do more than just calculate. Right? So here's the problem we're going to work on. It's a relatively simple problem where we have a heat load that's being intercepted by a fluid loop. So here's the fluid loop, and then the fluid is being cooled by a heat exchanger, so an air to liquid heat exchanger here, and the air is being blown across the heat exchanger coils by this blower. So what you need for this is a main diagram window that you can specify the heat load, and then several child diagram windows that allow you to specify things about the fluid loop, so the flow rate and the type of fluid, the heat exchanger here, so what's its size, what's the geometry, and then the blower, so what is the size of the blower and how fast is it going. And you'll probably want to use the component library to simulate the heat exchanger and the blower, and also provide options for the user to either run just a calculation, so simulation, and display the results on the main diagram window, and also some of the results related to the heat exchanger and the blower in the child diagram windows, but then also put a button on the main diagram window that allows the user to run a parametric study of something like, for example, blower speed, and then put the results of that study onto the diagram window with a plot. So that will be a fairly nice exercise to practice some of the things that we talked about, and I guess take some time to do that, and when you're done, or at least when you run into a snag, come back and we will run through the whole problem sort of together. So okay, so yeah, we're gonna go ahead and start this. I think I will put breaks in the YouTube video, so if you want to just skip to the part that you're interested in, that should make that kind of navigation easy, so you don't have to watch every step. But I am going to go through every step here, just in case there's questions about it. The first thing I'm going to do is set the unit system, so we'll just use a unit system directive for that. And the other thing I'm going to do is load the component library, because I know I'm going to need that for the blower and the heat exchanger. And then I'm going to start setting some inputs, and eventually these inputs will be taken care of in the diagram window, but just to get the simulation itself working, which is always kind of the first step, we'll set the inputs right here. Yeah, let's see. I'm going to set ambient conditions, so T ambient, maybe 20°C would be a good temperature, and P ambient is just 1 atmosphere. Then we'll go on to the blower. So let's see, I need to be able to specify the diameter and the speed of the blower, and then with those specified, we can go use one of the different blower models that are available in the component library. So let's set the diameter to 9 inches, and the speed, let's be a little careful here, because eventually I'm going to want to be able to switch between doing a calculation with a set speed and doing a parametric study in which I sweep speed. So I'm going to have a variable called mblower set, and maybe that's 1500 revs per minute. I think the blower model requires revs per second. And then if I am not in the parametric table, then I will set, so let's do $if not parametric, then I'm going to go ahead and set the blower speed to that end blower set. And if I am in a parametric table, of course, then I'll want to set the blower speed to whatever is set in the table. Yeah, I think maybe this would be a good time to solve. So F2 will solve this. I probably want to set some alternate units for some of these things, like the blower diameter, the blower speed, this one in particular probably I want to set. Atmospheric pressure, maybe we should set that in atmospheres. And atmospheric temperature is probably going to be convenient to set that in Celsius. Okay, so that all looks good. I think the next thing to do is set the inputs for the heat exchanger. And again, these will eventually, some of these will be set in the diagram window. So let's set the face area, W and H. So maybe 10 inches. And then we'll set H to 10 inches as well. And then I have to set the length in the flow direction. And if we're going to be using a blower, maybe we'll actually make it pretty long, so make it 24 inches. And then we have to set the, let's see what else we have to set. We'll go to the function information, and we'll go to the component library and find the heat exchanger we're going to use, which I think is probably that guy, heat exchanger 3. And maybe go ahead and paste it in here so we can take a look at it. So yeah, let's see. I gotta set the fluid type, which we'll do when we get to the fluid loop. Concentration, we won't need that. Flow rate for the fluid, again from the fluid loop. Temperature and pressure entering, we'll get to that. Air side flow rates, air side inlet temperature and pressure, and then these are actually about the heat exchanger. So yeah, W and H and L. And then we need to know the geometry, so I think that is the compact heat exchanger geometry core we're going to use, what the material is, the thickness of the fins, the relative roughness of the tubes, and then the number of tube passes. So let's go ahead and put in some reasonable values for that. So we're going to use I don't know, let's use FC tubes SCF-70-58J. So that's just one of the various core geometries that are available in the the compact heat exchanger library. And maybe we will assume that the heat exchanger is made out of copper. That's just for calculating the fin efficiency. We're going to assume that I think this is actually the tube thickness. The tube thickness is 1/32 of an inch. And what else do we need? We will put in a relative roughness of 0, and we will assume it's a single pass heat exchanger. And that should get us all the way through the heat exchanger specification. I'm going to comment this out, and we'll go ahead and run this and make sure everything looks okay. I'm going to set alternate units for these dimensions because I think that's probably going to be easier for the user to enter these dimensions in these alternate units. Some information about the fluid loop. So let's just say heat transfer fluid. And one thing is, what's the type of heat transfer fluid? So there's hundreds, literally, of heat transfer fluids in these. Let's just choose CalFlow AF. And then we will need the volumetric flow rate that it's being pumped at. So I don't know, maybe 2.5 liters per minute. We'll have to convert that to meters cubed per second. And yeah, the mass flow rate. To get the mass flow rate, I'm going to need the density. So density of the fluid at, we'll just say T equals T ambient. Density doesn't change very much. And it's incompressible, so we don't need a pressure. So m dot fluid is v dot fluid times the density of the fluid. Again, maybe, oh, I did something wrong here. Oh yeah, convert from liters per minute to meters cubed per second. So that all looks pretty good. I think we'll change the alternate units there to liters per minute, and I don't think we need anything else. All right, so at that point, we specified everything except for what the heat load is. So the heat load also needs to be specified, so we'll call that Q.HL, and I don't know, for starters, maybe 2 kilowatts. And we'll have to convert that to watts. And that should be good. So now we'll start the simulation. So let's think about the process, what I'm going to do, I think, is initially specify the states that I know. So the states that I know are the state of the air coming in, that's P ambient. I know the state of the air coming in is also at T ambient. That's what I'm pulling in from the atmosphere. And I'm going to assume that the fluid is at least near ambient pressure as well. So if we look at the schematic, I have to realize that this is going to be an iterative solution, right? So EASE is going to be good at this if I set it up right. So the first thing I have to understand is that I have to match up where the blower is operating on its head flow curve with the system resistance of the heat exchanger, the air side system resistance. So I'm either going to have to assume a mass flow rate and then make sure the pressure drop across the heat exchanger and produced by the blower match up, or alternatively I can assume a pressure drop and make sure the mass flow rates match up. Probably assuming the mass flow rate is going to be easier here. So I'm going to assume an air mass flow rate and then close up my iteration by making sure those two pressure drops match up. And then the other thing is, I don't know the temperature of the fluid in the fluid loop. I have to make sure that if I start here with the temperature entering the heat load and it gets hotter and then it goes through the heat exchanger, the performance of the heat exchanger is such that the fluid coming out of the heat exchanger is equal to the temperature of the fluid that I assume going into the heat load. So those are two, let's call them iteration variables, that I will need to initially set, and then we'll work through the calculations, and at the end I can remove those iteration variables and start with a good set of guess values in order to close up my equation set. So that's my process for doing this. So if we return to EASE, then I am going to set those two iteration variables. So I said that I wanted to set the temperature of the fluid entering the heat load. So something reasonable like, I don't know, maybe 30 C. It's got to be greater than 20 C, obviously. And then we'll set the air mass flow rate to something reasonable like 0.05 kilograms per second. And now I can sort of move through the rest of the calculation. So the first thing maybe I want to do is figure out what the performance of the blower is. So let's go ahead and go to the component library. And I want to go to, I think, blowers and fans. We're going to use a radial bladed centrifugal blower here. So that's fan 2CL. So I'll paste that in there. And then we can fill this in, right? So let's see. The fluid is air. The mass flow rate, I've at least assumed there's 0.05 grams a second. What would this be? This would be TA1. This would be PA1, not 2, 1. And then I've set the speed of the blower, and I've set the diameter of the blower. And this is going to predict for me the pressure leaving the blower, as well as the power provided by the blower, the temperature of the air leaving the blower, and if I'm interested in it, I can also get the blower efficiency. So this will allow me to calculate the pressure drop across the blower. That's going to be not pressure drop, sorry, pressure rise across the blower, PA2 minus PA1. And I should probably go ahead and solve that and make sure it works. So yeah, 185.2 Pascal. Let's go ahead and set some of these other units to make sure that I don't have a unit error. And then if I look in the arrays table, those are the temperatures and the pressures. So that all looks okay. I still have one more to set right there. So I'm getting 185.2 pascals. Maybe inches of water would be a better unit for that. So almost an inch of water. All right, so that's that. Probably go ahead and set my guess values. Always a good idea. And then let's see. Next thing I'm going to do is simulate the heat exchanger. So if I'm going to simulate the heat exchanger, I got to know the conditions of the fluid going into the heat exchanger. So the first thing I'm going to do is figure out the conditions of the fluid coming out of the heat load. So let's calculate the enthalpy. of the fluid entering the heat load. So what would this be? This would be the enthalpy at F equals of F dollar, T equals TF1, which I assumed here to be 30 degrees. And enthalpy also needs fluid pressure, so this would be P equals PF. And then an energy balance says that HF2 is equal to HF1 plus the heat load divided by the mass flow rate of the fluid. If I could type m dot, I think it's F, yeah. And then finally I can use that enthalpy and the pressure to get the temperature. So there's no temperature function for incompressible, so I'm just going to type that HF2 is equal to the enthalpy of F dollar at T equals TF2, and we will neglect the impact of pressure changes as they're not very important here. So hopefully if I solve this now, I will get, let's go to the arrays window. Yeah, this is the enthalpy, and then this is the temperature. So the temperature went up. Let's give it some alternate units. Yeah. Okay, so I guess all that's left then is to add in the heat exchanger, right? The heat exchanger will tell us what's the pressure drop of the air side across the heat exchanger, and it'll also tell us what's the temperature leaving the heat exchanger, and that'll allow us to finish our model. So let's see, the heat exchanger needs the fluid name. It needs the concentration if it's a brine. This isn't a brine, so I don't need to put that in there. The mass flow rate of fluid, what is this? This is TF, I guess 2 actually. Right? That's the temperature of the fluid entering the heat exchanger. This is the pressure of the fluid. This is air for us. We're just using air. This is the mass flow rate of the air. This is the temperature of the air entering. The pressure of the air entering is PA2. And then we have the size, WH and L, the core, the material, the thickness of the tube, roughness, and the number of passes. And what this is going to give us then is the temperature of the fluid leaving. So let's just call that TF out for now. The pressure of the fluid leaving, which I don't care about, so I'm going to get rid of that. The temperature of the air leaving, so I guess that's TA3. The pressure of the air leaving, PA3. The heat transfer rate in the heat exchanger, the effectiveness of the heat exchanger, the number of transfer units in the heat exchanger, and then the effectiveness of the fin, the efficiency of the fins in the heat exchanger. So hopefully, if I solve now, yeah, I'll get a solution. We'll go look at it, and yeah, everything seems to be working. I will verify some of these units, TL out, and that should be good. So let's update our guess values, and we will calculate the pressure drop across the heat exchanger. So I'll call it delta P AHX, and that's just the pressure of the air entering minus the pressure of the air leaving. And if we solve, we'll see that that pressure drop, so this is delta P blower, this is delta P heat exchanger, maybe again in inches of water. And of course, they're not the same. And the other thing that isn't being done quite right yet is the temperature of the fluid entering the load. The heat load is 303.2, and the temperature of the fluid leaving the heat exchanger is 317.2. So those two things haven't been adjusted to be right yet, but this is where we'll close up our equation. So I'm updating all the guess values. I'm going to go up here and comment out these iteration variables. And then down here, I'm going to say that delta P AHX has to be delta P blower. So that should hopefully give us the right air mass flow rate. And I'm also going to say that TF, what did I call it? TL out is going to be equal to TF1. So hopefully that'll give us the right temperature. And we'll cross our fingers and solve. And yeah, now we find that the actual delta P is 185 pascals, and then the actual temperature here leaving the heat exchanger is 45.2 degrees Celsius. So that's the simulation now. We should save that. With that out of the way, we can begin to start making the diagram window, right? So let's go to the diagram window, and this is the main diagram window. So I think the first thing I'm going to do here is paste in the schematic of the cycle. So let's see. I think I have that somewhere. Let's just go to the add picture button. It's that one right there. And if I click on the name, it'll bring up this dialog. And here's the JPEG that I have built already. So we'll pop that in there. There's my picture. So maybe I'll make this a little bit smaller, something like that. I probably also want to set up, maybe we'll specify the heat load here. So let's go ahead and put that in there as an input variable. So what is that called? Q dot heat load. Maybe don't include the variable name, but show the units. So that's right here. Probably that's about it for well, maybe the ambient temperature and pressure as well. So here's an input, T ambient. Let's get rid of the variable name. Let's show this in alternate units. Yeah. So 20 degrees Celsius and P ambient. So again, alternate units, 1 atmosphere. So there I can specify some things about the entire system right here. Of course, as I am adding these things, I really ought to be taking them away in here. So get rid of that. And I guess we got to get rid of these two guys as well. And I'll add a calculate button, just the normal calculate button. And if I put it in development mode, it should happily calculate now from the diagram window. Yeah. The other thing I might want to do here is set up my parametric table so I can do the blower speed sweep. So let's go ahead and set that up. I'll have a new parametric table. In the table, I will put, I don't know, maybe 6 points is enough. And we'll have, what do we put in here? Let's put TF1 and TF2. And then maybe also end blower. Yeah. So there's my table. We'll run end blower from, I don't know, let's set it in RPM and go from 900 to 1800, something like that. And now if I solve this table, it should go through and calculate the temperatures for every condition. I'll make a plot. So XY plot in which I include the blower speed and then this temperature and that temperature. We'll make it auto update. Add some grid lines. Maybe make a thicker line here and hit OK. Yeah, so there's my parametric study outcome. So let's change this to temperature in degrees Celsius. And this is the blower speed in RPM. And I guess it's obvious, but we'll put this in anyway. Heat exchanger inlet temperature is the top one. And then heat exchanger exit temperature is the bottom. So there's my plot, and I just have to put it onto the plot window here, or I'm sorry, the diagram window. So put it back in development mode, click the add plot, and then we'll actually just show the plot on the diagram window. And we'll put it maybe over here. Okay, and I probably also want to add a calculate button that runs the parametric study. So instead of calculate, maybe I'll call it vary blower speed. And instead of solve, we'll make this do solve table. And skip confirmations and hit OK. So now if I put it in application mode and run, it should go through all the runs in the table and then update this plot. Okay, I think that's that's good. Let's see. The other thing we were asked to do is make some child diagram windows that will allow us to specify things about the fluid loop, the heat exchanger, and the blower. So before we do that, let's actually put some of the temperatures on here that are useful. So we'll have some output variables for TF1 would be good. Yeah, TF1, and we'll hit OK. So that's the temperature right here. And then also TF2. So that's going to be the temperature right here. That's probably good enough for that. So now we're going to make some child diagram windows. And we have to remember how to do that. So here with the main diagram window in development mode, I'm going to define some hot areas. So that's probably the easiest way, so people can just click right on these components. So I want to emphasize where the hot areas are. So I'm actually going to put a box on here that will define the hot area. And then the properties of the box, I'd like it to be transparent with no fill. And probably that's good enough. So this is going to be my hot area for the blower. Let's do the same thing for the heat exchanger. And then finally for the fluid loop. So yeah, maybe right around this right here. Okay, so I'll hold down Shift and Control, and then I will define the first hot area to be coincident with that box that I just drew right there. And we're going to call this the blower, and we'll hit OK. And now I get my blower child diagram window. So in the blower child diagram window, I probably want to put a picture of the blower, and then also some input variables about the blower, and maybe some output variables about the blower. Yeah, okay, so let's go ahead and throw a picture of the blower on here. So I have one of those already made, so we'll put that on there. Make it bigger. And then we will add input variables that will allow us to set the diameter. Let me put that over here. And also will allow us to set the speed. So that's end blower set, if you recall. And then we will have, well, before we do anything else, let's go back to the equations window and get rid of those here so we're not double specifying them. And then we'll go back to that child diagram window and we will set output variables that include the efficiency of the blower. So I guess it's eta blower. And then also the, I don't know, the power of the blower, something like that, W dot blower. There, so that's the child diagram window for the blower, sort of all done. And hopefully at this point, if I put it in application mode, which I guess I have to do like that, I just have to do that here, and calculate, yeah, we should see that it calculates. And if I click on the blower, here's my, here's the information about the blower. Okay, back to application mode. Let's define another child diagram window. So this will be, again, a Control Shift. And I will make my hot area right here around the pump. And we will call this fluid loop. Okay, so maybe on this we will put a picture. So under the palette, here's a picture of a pump. If I hold the Shift key down, let's do that again. I can keep the aspect ratio the same as I stretch it out. So there we go. And probably we want people to be able to change the fluid, so this is a good place for a string list. So actually, this is also a good place to remind you of the substance information window. So if I open the substance information window and I go to heat transfer fluids, you can see the complete list of all the heat transfer fluids that are built into ease. So there's kind of a lot of them. And we could add as many of these as we wanted to this list. Let's just restrict ourselves to these 3 cal flows. So FG, AF, FG, and HTF. So I'm going to make an input variable for F dollar, and I'm going to use a string list. And we will include in the string list CalFlow AF, CalFlow HG, sorry, I think it's FG, and CalFlow HTF. And we'll hit OK. And let's get rid of the variable name and hit OK. And put it here. So that's a nice string list that lets you choose from different heat transfer fluids. So let's go to the equations window and get rid of, I guess actually both these, and we'll let the user specify also the volumetric flow rate on this child diagram window. So add another input variable, which is V dot in alternate units. And yeah, that should be good for that one. And then finally, I guess we have the heat exchanger here. So let's see, the heat exchanger, I'll control and shift, and we will specify this hot area. Call this heat exchanger. And maybe go to the palette and find a picture of the heat exchanger, or of a heat exchanger. So heat exchangers, maybe something like that. Pull it down. And we have to put in here a bunch of parameters. So let's see. I think this is all of this stuff here we're going to want to put in there. Although some of this stuff maybe isn't really worth putting in there. But for now, let's just put in the size. So the width, the height, so the face area, and the length. And go back to here and put heat exchanger. And here we'll put in the width, and the height, and finally the length, like that. And maybe some output parameters like, I don't know, maybe we want to know the NTU of the heat exchanger and the effectiveness of the heat exchanger. And that's probably good. So I think at this point we've completed the problem, so we can put everything into development mode. That's already in development mode, and then that. And we have a nice GUI for our program, so we can run a simulation. So if I want to change the heat load, I would change it here. If I want to change the heat exchanger, I would click on the heat exchanger and bring up that child diagram window. I can change things about the fluid loop, and I can click on the blower to change things about the blower. But that's that's pretty much it. I think probably the last couple things we'll do in this course is talk about a few more of the advanced controls and some other features of the diagram window, like tables and rich text edit. And then finally, we'll talk about how we turn these ease programs coupled with a diagram window into a distributable or an executable that can then be given to a user base, so that you have other people able to use these ease programs to do whatever it is they need to do to select equipment or whatever you have in mind there.